Next, we are going to study about the reactions of haloarenes. So, till now we were discussing about the reactions of alkyl halides. That means the reactions which the alkyl halides are undergoing. Now we are going to study about the reactions haloarenes or aryl halides undergoing. Okay. So, just like alkyl halides, haloarenes, the reactions of haloarenes there are three main reactions like in alkyl halides: nucleophilic substitution reactions, then reaction with metals, and electrophilic substitution reactions. So, in this video, we are going to study about the nucleophilic substitution reactions and reaction with metals. So, just like in alkyl halides, what is meant by nucleophilic substitution reactions? Yes, it is the halogen atom present in alkyl halide or aryl halide will be replaced by another nucleophiles like OH minus, Cn minus, etc. So, before we start all these, what is meant by aryl halides? Yes, halogen directly attached to benzene ring. Isn't it? So, halogen, aryl halides, how we can represent generally? X directly attached to benzene ring. Now, alkyl halides means what? Rx. So, alkyl halides can very easily undergo nucleophilic substitution reactions. But aryl halides are less reactive. They are extremely less reactive towards nucleophilic substitution reactions. Means, if we treat with aqueous NaOH or aqueous KOH from aryl halides, if we treat with aqueous NaOH or aqueous KOH, it is very difficult to replace this X by OH or X by any nucleophile. So, why it is very difficult to replace the halogen which is directly attached to benzene ring by another nucleophile? So, why aryl halides are less reactive towards nucleophilic substitution reactions? So, that is a very important question coming here. Repeated board question. Aryl halides are extremely less reactive towards nucleophilic substitution reactions. Why? Repeated board question. The first and the main reason is already we have learned in class 11, in aryl halides there is resonance and we know the resonating structures also. So, when we draw the resonating structures, if you look at the first structure, when we attach chlorine directly to benzene ring, we know that in chlorobenzene or in halobenzene, on halogen atom we have 6 electrons or 3 lone pairs. So, when they attach to benzene ring, this lone pairs will be in conjugation with the benzene ring and the carbon halogen bond gets a partial double bond character. If you look at the resonating structures in structure 2, 3 and 4, you can see partial double bond character in this carbon chlorine bond. So, what is the first reason? In haloarenes, the electron pairs on halogen atom, they are in conjugation with the pi electrons of benzene ring. So, CCl bond occurs a partial double bond character due to resonance, and as a result we know that when you compare the strength of a double bond and single bond is always stronger than a single bond. So, due to this partial double bond character of CX bond in haloarene, it is very difficult to break the carbon halogen bond, because we know that in nucleophilic substitution reactions there is breaking of CX bond and formation of new carbon nucleophile bond. So, if there is partial double bond character, it is very difficult to break the carbon halogen bond in haloarenes. So, resonance is the first reason for resonance, and the partial double bond character of CX bond is the first reason why aryl halides are less reactive towards nucleophilic substitution reaction. Now the second reason is the difference in hybridization of carbon atom in CX bond. If it is an alkyl halide, we know that X will be attached to an alkyl group, and in alkyl, if it is an alkyl halide, X will be attached to sp3 hybridized carbon. But in aryl halides, X will be directly attached to benzene ring, and what is the hybridization of that carbon? sp2. So in aryl halides, X will be attached to sp2 hybridized carbon, while in alkyl halides, X will be attached to sp3 hybridized carbon. We know that when we say about the electronegativity order, sp hybridized atoms or sp hybridized orbitals are more electronegative than sp2 than sp3. So when we compare the electronegativity of sp3 and sp2 hybridized carbon atoms, sp2 hybridized carbon atoms are more electronegative than sp3. That means high electronegativity means those carbon atoms can attract the shared pair of electrons towards itself. So what happens due to the high electronegativity of this sp2 hybridized carbon? In haloarenes, we know that X is directly attached to benzene ring, and this carbon is, now we know that it is sp2 hybridized. And this sp2 hybridized carbon being more electronegative, what happens? These shared pair of electrons will be tightly held by this. This carbon atom, this sp2 hybridized carbon atom will be tightly holding this shared pair of electrons. And we know that during a nucleophilic substitution reaction, the halogen will be leaving as X minus with this bond pair of electrons, isn't it? So due to the high electronegativity of this sp2 hybridized carbon, X will not be able to take this shared pair of electron, and it won't be eliminated as X minus or leaving group. So the second reason is due to the difference in electronegativity. And since this carbon is more electronegative, the CX bond length, the CCl bond length in haloalkane is 177, but in haloarene it is 169. So the CX bond length in haloarene is shorter. Shorter means shorter the bond, stronger will be the shorter the bond length, stronger will be the bond. So CX bond in haloarenes will be more stronger than the CX bond in haloalkanes. So very important point, it is very difficult to break the shorter bond than a longer bond. Therefore haloarenes are less reactive towards nucleophilic substitution reactions. Now the third reason is instability of phenyl carbocation. We know that if a halide is following SN1 mechanism, SN1, the order of reactivity depends on the stability of carbocation forming. So if aryl halides are undergoing SN1 mechanism or following SN1 mechanism, the carbocation forming will be phenyl carbocation. If X is leaving as X minus, it will be forming phenyl carbocation, and this is highly unstable. If the carbocation formed is highly unstable, the reactivity will be very, very less. So the next point is instability of phenyl carbocation. So there is no chance for SN1 mechanism. Now the last reason is the repulsion between, because we know that aryl halides means halogen is directly attached to benzene ring, and nucleophilic substitution reaction means if this halogen, if we are replacing by a nucleophile, we know that nucleophiles are electron rich species. Haloarenes means they are also electron rich because benzene ring is highly rich with electrons, delocalized electrons. So what happens? The incoming nucleophile is electron rich. Aryl halides are also electron rich, so there will be repulsion between these two species. So the next reason is the repulsion between the electrons rich nucleophile and the electron rich arenes. So these are the reasons, the very important 4 points why aryl halides are not undergoing, or they are less reactive towards nucleophilic substitution reactions. Once again, the first reason is due to resonance, partial double bond character, difficult to break. Second reason, difference in hybridization, since it is sp2 hybridized, more electronegatives, more tightly will be held more tightly, so bond length will be shorter, so it will be more stronger. And the third reason, instability of phenyl carbocation, and the fourth reason is electron-electron repulsion. So what we can conclude from this? If a halogen is directly attached to benzene ring, can we replace that halogen by a nucleophile like OH minus or CN minus? No, it is very difficult. Only if we apply extreme conditions, under ordinary conditions or ordinary room temperature conditions, it is very difficult to replace halogen which is directly attached to benzene ring. So if we apply extreme conditions only, we can replace halogen directly attached to benzene ring. So that is the next section, that is Dove's process. Dove's process is actually a method showing how we can replace chlorine which is directly attached to benzene ring by OH group. So it is a conversion of chlorobenzene to phenol. So it is a replacement of chlorine directly attached to benzene ring by OH group, and the reagent is usually for a nucleophilic substitution reaction, the reagent that we use is aqueous NaOH or aqueous KOH. If we want to replace by OH, isn't it? Either we can use aqueous NaOH or we can use aqueous KOH. But here, since the chlorine is directly attached to benzene ring, we have to apply extreme conditions, that is, along with aqueous KOH, we have to give a temperature, we have to heat to 623 Kelvin, and the pressure should be 300 atmospheric pressure. So chlorobenzene will be treated with aqueous NaOH at 623 Kelvin and 300 atmospheric pressure. Only under this condition we can replace Cl by OH, otherwise it is very difficult. So first we will be getting, instead of OH, we will be getting ONA because we are using NaOH, a base. So instead of phenol, first we will be getting sodium salt of phenol, that is sodium phenoxide, which on acidification, on treating with any acid, ONA will become OH. So this is the equation for Dove's process. Chlorobenzene will be treated with aqueous NaOH at 623 Kelvin and 300 atmospheric pressure. We get sodium phenoxide, followed by acidification we get phenol. So it is a conversion of chlorobenzene to phenol. So very important reaction, Dove's process. It is a conversion of chlorobenzene to phenol. Now, what is the effect of, if there is any minus psi or electron withdrawing groups coming in this benzene ring, will there be any effect on this nucleophilic substitution reactions? That we will see. Which are the minus psi groups? Yes, NO2, then all the carbon containing functional groups, carbon starting functional groups like aldehyde, ketone, acid, etc. So nitro group is a very good example for a minus psi group. So if there is any minus psi group, nitro group is a very good example for minus psi group. So if a nitro group is present in the, along with chlorine, if a nitro group is present in the benzene ring, will there be any effect on this nucleophilic substitution reaction? Okay, that we will see. The presence of electron withdrawing groups, that is minus psi groups like nitro group, at ortho and para positions will increase the reactivity of haloarenes. So if there is any minus I group present in the benzene ring, the reactivity of haloarenes will be high towards nucleophilic substitution reaction. The very important reason why. Why? Because minus I group means they are electron withdrawing groups, isn't it? So we know that one of the main reason for the aryl halides not undergoing nucleophilic substitution is electron repulsion. Haloarenes, the benzene ring is highly rich with electrons. The incoming nucleophile is also electron rich, so there will be electron repulsion. So if there is any electron withdrawing groups present in benzene ring, for example, along with chlorine, if a nitro group is present at the para position or ortho position, what happens? Being an electron withdrawing groups that will withdraw electrons from the benzene ring. So what happens on the electron density of benzene ring? The electron density present in the benzene ring decreases. So the incoming nucleophile will be experiencing only less repulsion from the benzene ring. So it will facilitate the nucleophilic substitution reaction. Okay, so the reason is because they withdraw electrons from the benzene ring and thus facilitates the attack of nucleophile on haloarenes. So we will see. If there is one nitro group, what happens? If there is two nitro group, what happens? Okay, so if there is one nitro group present at the ortho position, if there is no minus I group and if only chlorine atom is present in the benzene ring, we know the condition, isn't it? We have to take aqueous NaOH at 623 Kelvin and 300 atmospheric pressure. But if there is one nitro group present, so no need to apply the high pressure. And the temperature is also reduced to 443 Kelvin. So we need to treat with aqueous NaOH at 443 Kelvin only. What happens? Cl can be replaced by OH. So the condition, we can reduce the extreme condition. Reactivity is increased due to the presence of one nitro group. Now, if there is two nitro groups, one is at the ortho position and the other one is at the para position. See the condition? Treat with aqueous NaOH at 368 Kelvin only. The pressure is no need to apply very high pressure and low temperature only we need to apply. The temperature is again reduced 443 to 368 Kelvin only we need to apply. Okay, again we can replace Cl by OH. Now if there is three nitro groups are present at both the ortho positions and the para position, no need to use aqueous NaOH, no need to apply high temperature, no need to apply high pressure. We need to just either use warm water or just heat with water. If we treat with warm water, very easily we can replace chlorine by OH. That much highly reactive will be the haloarene if there is three minus I or electron withdrawing groups are present in the benzene ring. So what we can conclude from this, if there is minus I or electron withdrawing groups present in a benzene ring, the haloarenes can easily undergo nucleophilic substitution reactions. And what about the position of this minus I groups? They should be present at ortho and para position, because from the resonating structures it is clear, because due to resonance in haloarenes the electron density is increasing at, if you look at the resonating structures, we can see that when a halogen is directly attached to benzene ring, there is increase in electron density at ortho and para positions. So that is why the nucleophile is experiencing maximum repulsion. So maximum repulsion will be at ortho and para position. So if there is any minus I group at these positions, the rate of reaction, the rate of nucleophilic substitution reaction can be increased. Under normal conditions, it is very difficult to replace halogen which is directly attached to benzene ring by a nucleophile. Only if there is -I groups present we can replace, otherwise apply extreme conditions. Now the second type of reactions the haloarenes undergoing is the reaction with metals, and we have only the reaction with sodium metal. The first reaction is Fittig reaction. When we say about the reaction with sodium metal, it is similar to Wood's reaction. What is the reagent for Wood's reaction? Metallic sodium in dry ether. In Fittig reaction also the same reagent we are using, metallic sodium and dry ether. In the Wood's reaction is actually the reaction that the alkyl halides are undergoing. 2 moles of alkyl halides are undergoing Wood's reaction, but here the difference is 2 moles of aryl halides are undergoing reaction. So Wood's reaction only alkyl halides, Fittig reaction only aryl halides. Okay, 2 moles of sodium, metallic sodium in dry ether gives compounds in which 2 aryl groups are joined together. How? We will see now. The tip is same as that of Wood's reaction. The product we can write same as we write the product in Wood's reaction. So here also mark the X attached carbon. This is the X attached carbon and this is the X attached carbon here. Connect these 2 carbon atoms using single bond after removing halogen. And how we are removing the halogen here? As 2NaCl. So 2NaCl will be removed. Now we need to connect one benzene ring, another benzene ring. Connect these 2 carbon atoms using a single bond. Or this we can draw in another way also. Both are same. And they are known as biaryls or biphenyl. Biphenyls or biaryls. So they are also hydrocarbons like Wood's reaction. The only difference is 2 aryl halides are undergoing Fittig reaction. So in Wood's 2 alkyl halides are undergoing to give hydrocarbons. Here 2 aryl halides are undergoing to give biphenyls or diphenyls. Now the second type of reaction is with metallic sodium is Wood's Fittig reaction. So here also aryl halides are undergoing, but the difference is in Wood's Fittig reaction, it is a combination of Wood's and Fittig reaction. Because in Wood's, as we said, only 2 alkyl halides. In Fittig reaction 2 aryl halides. So here 1 molecule of alkyl halide will be reacting with 1 mole of aryl halide in presence of metallic sodium and dry ether. Here also we are getting hydrocarbons and they are known as alkyl arenes. So Wood's Fittig reaction, the products are known as alkyl arenes. They are also hydrocarbons. So here also same way to write the product. This is an alkyl halide and this is an aryl halide. Reaction with metallic sodium in dry ether. Mark the X attached carbons and connect these 2 carbon atoms using a single bond. Very easy to write the product and remove the halogen as 2NaCl plus benzene ring. Connect these 2 carbon atoms using single. So we are getting toluene as the product. So this is an alkyl arene because an alkyl group is also present and an aryl group is also present here. Same way how we can write the product of this. This is the X attached carbon. This is the X attached carbon. Connect. So we will be getting it as benzene ring. Connect this carbon with CH2. So how to write it as CH2, CH3 or ethyl benzene. Another, all these are hydrocarbons and we are getting 2NaCl. So if you study Wood's reaction, very easy to write the products of Wittig and Wood's Wittig reaction. So Wood's reaction is the reaction only alkyl halides undergoing. Wittig reaction is the reaction only aryl halides undergoing. Wood's Wittig reaction is the reaction aryl halide, both alkyl halides and aryl halides can undergo. In all the three reactions, the reagent is same, that is metallic sodium in dry ether. And we are getting everywhere, we are getting hydrocarbons. Okay.